Hello, everyone. Konbanwa. I'd like to take the opportunity to share some thoughts of mine regarding errors in Swift. Before I start, I'd like to make clear that the word error, by that word error, I'm not just referring to the error type, but to an all-encompassing view of anything in your code that you may consider as going wrong or not the ideal code path. よろしくお願いします. So, I'd like to start off by stating the motivation that drives this presentation. We want, first of all, code that is stable and behaves correctly. I mean, who doesn't want that, right? So, we want code that does what we intend for it to do, and for that to happen all the time. This allows us to continue delivering new features and improvements at a fast pace. Also, we want to anticipate, as much as possible, any and all quote-unquote unexpected errors, and minimize the impact this has on the user. For example, if we aren't able to read part of the user's data from the database, we wouldn't want to just crash and give up. In cases where the user cannot avoid causing an error, you want to be especially careful of this. Code, say, to be run on launch to render your main view is one example. Any kind of automatic process that the user doesn't have direct control of, say, to sync data over the network or clean up stale data, then it's even more important to do so because it may result in a denial of service. We also don't want to resort to having the user contact customer support and then having to ask the user to reinstall the app. Not only is this an awful experience for users, it can mean that users lose data that's important to them and lose trust in your app. So with that in mind, I'd like to start off on the first point about writing correct code. There are many topics you could discuss regarding how to go about achieving this. How to write maintainable code, how to write testable code, with the goal of assuring the correct behavior doesn't become incorrect in the future. But for today, I'd like to talk briefly about input. In order to write correct code and prevent errors from occurring, we need to be able to handle any and all input. It helps me to break input down into two types: explicit and implicit. Explicit input, by nature of being explicit, is going to stand out to the reader and more clearly communicate intent. Explicit input is going to be the parameters to your functions. You also have this self thing in methods. In Swift, self is implicitly passed. So in that respect, it's easy to overlook. But I think conceptually self is more of an explicit input. Implicit input is any other data accessible to a function and is usually referred to as state. So in this very simple example, the parameter ID would be explicit input, and settings would be implicit input, as it's not a part of the method signature. So, state typically consists of variables and constants at global scope. Any outer scope accessible to a function can be a potential source of state. Singletons fall under this category. If your function depends on the values of any of these, the output can differ, even with the same explicit input. On the other hand, functions that don't depend on or affect state of varying degrees are known as pure functions. I won't delve into this topic, but I will mention that there has been discussion lately in the Swift evolution mailing list to get support in Swift for declaring functions as pure. This would allow the compiler to enforce the function's pureness at compile time. Next is what I call temporal state. This is the state of the program being executed at any time. This comes more into play when dealing with concurrent programming, but is still a useful concept. It's partially defined by the order of statements in imperative code. Because the order of code tends to be taken for granted, I would classify temporal state as being mostly implicit. The order that code needs to be run can be made more explicit. The most basic way would be to write a comment to the human reading the code. For example, A must be called before B, or very bad things will happen. If you want to communicate this to the compiler as well, you should make your code not compilable when rearranged in any other order. Let me show you what I mean with an example using concurrent programming. If you're not familiar with Grand Central Dispatch APIs, this is going to execute these print statements independently of each other. The order is not defined. You can think of the possible states of execution order being multiplied as the threads of execution interweave each other in differing patterns. So you can imagine that before this code, there was a nice stream of execution. And as we reach this code, we split off into 3 streams. The print statements share the same serialized output, so they interact. So since there are 3 places to fill, that gives us 3 factorial or 6 potential outcomes. Here I'd like to illustrate the same concept, but this time without currency. Nothing much interesting is going on here. Each statement here is evaluated in a top-down order. Some of the values are used as arguments for other function calls later on. So there is a relationship enforced here by the compiler. I couldn't place the line for let's see first, even if I wanted to, because we don't have the value of A yet. And then we have this glaring function call smack in the middle. What's it doing here? Since it doesn't have any input or output, we assume that it must be affecting state that affects the output of the code around it. We just don't know unless we understand what makes do something interesting. And finally, I'd like to mention input or state from the real world. This isn't a distinct type of state, but rather describes a property of it. What makes it worth mentioning is that, for one, its complexity can easily get out of hand. And 2, because the state usually originates from your own code, we tend to make assumptions about its values. For example, we may assume that we only stored non-negative numbers in a given database field, because we made sure not to insert a negative value. However, are you sure the behavior has been like that for all past versions of that code? Maybe at one point, someone thought it'd be clever to store -1 or null to indicate that maybe the data was out of sync. Maybe there was a bug at one point. Could this code be run on data from the output of future versions of your code? Do you want to be able to handle data fidgeted with directly by the user? Yeah, you can see how easily this will get out of hand. Any changes to code handling this kind of state shouldn't be modified haphazardly. So I'd like to give a simplified example of a bug I actually created recently. In the app line, there's a feature called theme. It lets the user change the look of the app. My task was to migrate the format of the string format of the setting that holds which theme is currently in use by the user. As you can see here, the setting is stored in user defaults. So I added code that gets run when the app is launched for the first time on the new version, loaded this setting from user defaults, and I put the new format back in. Simple enough. But I soon found out there was a problem with this code. The app was launching with the default theme. You would think maybe I botched parsing the old format, but following launches used the theme that was previously in use. It turned out here that the theme subsystem was inadvertently being initialized before my migration code. Since the new version of this code expects the newer format, it failed to initialize correctly with a migrated value from user defaults. However, once the migration code ran, subsequent launches found the setting and it initialized properly. So we can say that the bug was created because of the shared state and ambiguous temporal relationship or dependency between the migration and the theme subsystem initialization. So how do we go about fixing this? And how do we prevent this from breaking again in the future? Well, one way is to make the relationship between the two explicit at compile time using the type system. Very plainly put, if you don't have an instance of a type, you can't call a function that requires it as input. Using this fact, we can create types that represent a transition in state. Requiring instances of those types as parameters to our functions allows us to specify this state as a prerequisite to calling the function. Going back to the code, we could fix this by representing this in the type system. We can do this in several ways, but a very basic way would be by creating a setup complete type and adding it to the initializer's parameters. All that's left is to create this instance of setup complete only when that state occurs, and then pass it along. Now I'd like to switch gears and talk about the actual error type in Swift. More specifically, when to use the error type over an optional and vice versa. An optional type, when used as output, typically represents a right or wrong value, or just the presence or absence of a value. When used as input, it tends to represent optional semantics, as the name implies. So the presence of the value isn't required to proceed. Swift syntax makes it fairly easy and straightforward to safely handle these optionals. So optionals are the go-to choice. The error type has similar semantics of wrong or unable to complete successfully. I find the obvious and most common use of error types is for fatal or catastrophic errors. Well-known examples of these would be trying to connect to a corrupt database or failed I/O. The way the syntax works for dealing with thrown errors is that it leans towards ease of use for writing the happy path, and less so towards setting up how to catch and deal with these errors. I think I'm right in saying most Swift programmers don't like having to move their cursor back and forth to wrap their code in two catch blocks, or even having to mark a method with throws. Stated another way, I think this means that errors are something that occur infrequently to the point that we feel like it's a hassle to even have to consider. And when they happen, they're bad enough that we usually need to abort what we're doing. This thing that we're doing is something we have to define. And we define this by setting up do and catch statements. So kind of working backwards from this, I find it helpful to use Swift's error type to handle problematic situations that have a low probability of occurring. To give you an example, I had written a struct to represent chat IDs. These IDs are usually represented in a specific string format, and certain assumptions are made regarding it. So the struct validates the string and can provide some additional information on the type of chat it represents. At first, I represented this in code as a struct with a failable initializer. This is a very standard and reasonable approach. However, the more my team and I used this chat ID struct, a pattern started to emerge. In some situations, people would correctly handle the optional. In these cases, they would return early and perhaps even log the error. However, more often than not, people would take a look and say, this value is coming from the database. It's a trusted source. Of course it's going to succeed, and would proceed to force unwrap the optional. So I decided that we should be using try statements here instead. Ideally, there should already be an error handling context somewhere, which is going to be your do catch block. In our case, this would be where we started processing a server response. If there isn't an ideal setup like this, we're going to wind up making the consumers of this API jump through hoops to eventually convert this to an optional. Since I'm deciding to use the error type based on how it will be handled, there is a slight coupling here. So I find that Swift's error types are most useful for types where there is knowledge of how its errors will be handled. In my example here, I found that I could provide custom errors that I could throw to ease troubleshooting later. However, just knowing why I couldn't parse a chat ID string wasn't good enough. I wanted to know the overall context in which this occurred for error monitoring purposes. And this overall context also coincided with my do catch statements. So this is the type of situation that I feel the error type is best suited for. So wrapping things up, I'd like to say be cognizant of input-output flow. Knowing it and its source helps you judge what's important enough to need more explicit modeling in code. This will lead to code more robust to erroneous input and input values that may be easily overlooked. Be aware of code critically important, code that we can't afford to be nonchalant about. This will guide how robust we write such code. When dealing with problematic input, if the problem is generic enough to the point that you can't provide diagnostic information of any use, then use optional. However, if, for example, there are several failure points, or you want to add more context to your errors using error propagation, and the context is available with your catch statement, then the error type works well. Thank you. ご清聴ありがとうございました。
Good talk. Thanks for it. Learned a lot. What's your opinion on using stuff like fatal error in situations where you really can't handle anything but crash?
Yeah, that's a good question. It's kind of hard to say without a concrete example. But in my code, personally, I do use the exclamation point to force unwrap from time to time. But it's in cases where I feel it's because if I were to proceed, it would be a programmer error, and that it's something that's easily detectable during testing, that it's not like down some branch of code that hardly ever gets run. And so I would like to know about it rather than silently ignoring it, or who knows what would happen.
What do you think about the result time?
I knew someone was going to ask this question. Yeah, I use result for, well, very limited part of our code just for the initial server response. But our code isn't, I wouldn't say it's very functional at this point. And I said the F word. But I would think if you were going to propagate that on further, then yeah, or use a more functional approach, then yeah, result is also it's a good choice. Yeah.
Okay. Thank you, Chris. ありがとうございました。